Alrighty, all you YouTube subscribers out there. So I know all. You know what? What you want? I got like 240. Yeah, but only like 3 people watch a video. Anyway, okay, so this one right here, we're gonna find parametric equations corresponding to the equation of y equals x squared minus 4. So the big thing that we did is, anyone recall? What do? We got to change the xy's, right? Okay, so x equals t. So if x equals t, what do we get? I have that part, but I also have another part too, which I have to try and do. So I'm going to have a y of t, and I also have to have an x of t. Since I know that this is going to look like this, so it's going to have x, come on now, brain work. X of t is equal to t, and y of t is equal to t squared minus 4. Are you guys looking for the notes?
Yeah.
Oh, I'm sorry. Totally forgot about putting it out there. All right, that's what we come up in my parametrics for this. Yes? No? Same as what we did on Friday, right?
Yeah.
Okay, so we have those. That's basically it. That's all I need. All right, finding parametric equation for an object in motion. Okay, where the parameter t is in seconds and the motion around the ellipse is counterclockwise and begins at point 2, 0 and requires 1 second for a complete revolution. The motion around the ellipse is clockwise, begins at the point 0, 1, requires 2 seconds for a complete revolution. Okay, so part A. First thing for part A. So what are we going to have for this? So I need to start by rewriting this. So if I rewrite this in terms of t, thank you. Rewrite it in terms of t. So if I rewrite it in terms of t, what am I going to have? So I'm going to have. So I know a couple things about this. Let's delve into this a little nasty. Isn't this going to be x over 2 squared, right?
Yeah.
Okay. Okay. That right there is always good to know. So I have that piece right there. So now, is the next page blank? Yes, it is. Okay, so I have all right, so now what do I need to do? So my x values, right? So if I know that my x is equal to, I gotta change it to the t's, right? So my r value in this, remember from my formula the other day, my r value is gonna be 2.
Yeah.
So it's gonna be x of t is equal to 2 cosine of t, right?
Yeah.
Cosine of t, because if you guys remember, when I did this, this is a Pythagorean identity.
Yeah.
I'm going to go back to this for those people that were not. Here it is right here. My Pythagorean identity that we have right here. So it's sine squared, or cosine squared t plus sine squared t is equal to r, capital R squared. So parametric equations are equations that are rotating around in a circle in my graph. So since I have it set up in that format, so my r value was 2, so now I could actually change it to 2 cosine. So, all right, you guys got this? Okay, I'll give you a second. You You got it?
Yeah.
Okay. No. Huh. Okay. So we have that. So now what about that y? Okay.
Yeah.
So y of t is going to be equal to sine of t, right? Because my r value in that case is 1, right?
Yeah.
Okay. So I know a couple things about this. So I know in my first part right there, it says that it makes a circle when? How long does it take to make a circle? It's going to be how long?
1 whole second.
1 second. So in the first one, in part A, it makes a circle in 1 second. So I know that is going to be 2 pi per second, right? So my speed is going to be, come on. So for this, I know since before we didn't have parameters of time in which telling us how fast it was going. Now we do. So now what is that going to do? What is that going to change? Coefficient of t, right? It's telling me how fast that's going. We didn't have that before in any of the problems. Now we actually are adding that in. So that's going to be coefficient of t. So now in this case right here, it's going to be 2 pi, right? For this. So I'm going to have 2 pi for those. So that's going to help me out. So I'm going to set that up. So it's going to be x of t 2 cosine of 2 pi t, right? And y of t sine of 2 pi t. So it's the speed in which I'm actually traveling for there. And it's going to be from question? Please, if you have a question, speak up, because this is the basis of all the rest of the stuff that I'm going to be doing. Okay. All right, let's take a look at the other one then. So part B says, part B says the motion around the ellipse is clockwise, begins with the point 01, and requires 2 seconds to complete a revolution. Okay, so now think about it. It's 2 seconds to complete a revolution. How fast is it going to go?
Pi over second.
Pi?
Over second.
Yes, pi per second, yes. Pi over second. So it would be 2 pi, right? So 2 pi, so one circle in 2 seconds. So it's pi divided by 2. Or I'm sorry, pi over 2 divided by 2. So it's the whole thing, which is 2 pi divided by 2, which is going to give me just pi, okay, per 1 second. So it's pi per second in this case. So that's going to give me the speed in which that this is traveling, right? So every 2 seconds, it's going to make a whole rotation. So now, in this case right here, what's the difference about this one? It's starting at 0, right? So how would I make this one start at 0? Start at sine, right? So to do that, I would start that one at sine. So my x of t would equal what? Would it be sine or would it be 2 sine?
Sine, because you want to double the cosine stuff. Because it was 0, 1, not 0, 2.
All right, go. Let's go back and look at the question. Motion around the ellipse is clockwise, right? So we're going backwards now, right? So we're going backwards from what we have, okay? And begins at the point 0, 1, so that means I need to have my sine, right? Okay, so now to get that requires 2 seconds complete revolution. Okay, so I am now going to start this with the, since I am supposed to start there, I should have the 2 sine. Of t, because I'm actually referring to the first value, my x value there, and then my y of t would be cosine. And then the speed of which that this is going to be my pi, right? So let's go ahead and add that into my pi. So added my pi, so x of t is equal to 2 sine of pi t. Y of t is equal to cosine of pi t, and it's going to be so I'm going to have bounds from there to there. How long does it take to actually go a whole thing? 2 seconds. Mm-hmm.
So if it's clockwise, then it'll be sine, and then counterclockwise is cosine.
Yeah, I changed that up because I want it going in the other direction. So if you think about it, so just think of the numbers now, okay? Think of the numbers. So if I have a graph, I'm starting at 0, 1, right? So starting at 0, 1, okay, so I'm starting here. So now let's go ahead and plug it in. So this is going to give me, what do we get? So we start with that value. I get, for the x value, let's see, I get bam, 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 bam. What do I get?
Starting at,
Oh wait, no, there's pi inside.
t equals 0, you get 0.
Yeah.
Okay, so starting at 0, sine at 0, I get 0, right?
Yes.
Okay, so I get 0. So now, next one is going to be, let's go 1. I'll actually do the y value now. Okay, do the y value,
Which is cosine of 0,
which is
1.
1. There we go. So we get that. So now I have that coordinate correct, right? Okay, so the next one. Let's plug in, let's do 1. Actually, no, I don't like 1. Let's do pi over 2. Crap, can't do pi over 2.
1/2. No, don't do anything with pi because it's going to be cancelled.
Yeah.
You're going to get a
1/2. Yes, 1/2. So if I do 1/2, that's going to be pi over 2. Sine of pi over 2 is
0. So it's going to be x is 0.
no.
Sine of pi over 2.
That's going to be 1, right?
Yeah.
So this is going to be 2. And then cosine at pi over 2 is 0, right? So it's going to give me this point right here. So that's how it's going this way now. So as I'm plugging in numbers, okay, I did half, and the next one's going to be 1. So if I plug in 1, what is sine at 1? 0,
Yeah.
right? So I'm going to come back over here. It should be 0, negative 1, right?
Yeah.
Okay, so now let's plug in 1. Cosine at 1 is negative 1, right? So negative, okay, negative 1. So there we go. Now do you see how it's going in the right direction now?
So then how would it look if it was the counterclockwise, like it was rotating?
So counterclockwise, let's look at the previous one then. All right, let's go ahead. All right, so first one, 0. Let's plug in 0 for my x coordinate. 0, cosine of 0 is
1.
times 2. So I get 2 here. The y value, 0, right?
Yeah, so that's just
So it's 0, right? So I'm starting there, right? Comma 0. Now let's go ahead and let's plug in, what do I need here? 1/4, right? Let's do 1/4. So 1/4 is going to make this one pi over 2, right?
Which is 0.
Cosine at pi over 2 is 0. So I'm going to have 0, and then do the same thing. This is going to be sine at pi over 2 is 1.
And then it keeps going.
Now do you see how this is actually changing now for this? So as we're plugging in, are you okay?
I am okay.
Okay. I'm just making sure you're giving me that weird look again.
No.
Eh,
Did you see what
What if that's just how his face is?
like, same look when I said Americans put pineapple on pizza, and he's like,
You know you're supposed to speak
That
English
look
in
is
class.
I
You know you're supposed to
love
speak English in the classroom?
huh?
You're supposed to speak English in the classroom?
I know, right?
Yeah.
I'm sorry.
I can't understand that.
Yeah, I don't know what you're saying.
That's alienating.
Okay. All right. Does this make sense now? We're going around as we're plugging in for the times. All right. Cycloid. Suppose a circle rolls along the horizontal line without slipping. As the circle rolls along the line, at point P, the circle traces out a curve called a cycloid, as shown in the figure. Deriving the equation of a cycloid rectangular coordinates is complicated, but in terms of parametric equation is relatively easy. All right, so any point in which that we can find on here, we're able to do a math on this one. So it's always going to be above. Okay, it's always going to be above. So it's going to go here, and it's going to come back down like this. Then it's going to bounce back up. Kind of like that. And it's going to keep doing that as it's rotating around. And then it comes back up.
So why do we have to worry about slipping?
Because when we get into the physics of this, there's certain things that you have to deal with. Because we're just talking about with no, okay, I'm just going to throw out like that hypothetical problem that all calculus students complain about. Okay, you're driving down the road at 44 miles an hour. Okay, you decide to throw a water balloon out, and at the speed at which that you are driving, it's 44 miles an hour. What is the speed of the balloon after 2 seconds given wind resistance? So because there's going to be wind resistance that you have to actually take into account, mathematically, with no wind resistance, you can get, a nice equation to say exactly when it's going to hit. But we also have wind resistance.
Gravity.
We have gravity. We have stuff like this, like slipping right here.
slipped on air.
And especially in this case right here, we have tires. Whenever you're like, let's say for instance, you get a job, you know, at one of these car companies and you design some type of transmission. That's one of the things that you have to play a big part into your math. Is the weight of the vehicle going to be too light to cause the tires to start slipping when it engages? So like peeling out. If there's a lot more horsepower than what you have, you know, the weight. So the weight gives you friction with the road, and that contact is what keeps it going. So if you're still peeling out in like 60 miles an hour, guess what? You don't have contact with the road. You now have, you know, it's slipping. So you don't actually have your tires turning at that speed. Your vehicle is not turning at the same speed. Does that make a little bit better sense?
Yeah.
Yeah, so because we're dealing with this, it has to do with stuff like that. We're not including the slipping. So we're just doing the pure math. Eventually you're gonna get into some slipping. You know, you put your foot on the acceleration and then you get the third derivative out of it, and so those are the things. You get the jerk.
You jerk, yeah.
The jerk. Okay. Alright, so parametric equations cyclone are here. Okay. A is right here. The radius of the circle. Say yes. Okay, good. Okay. Parentheses. T minus sine of t. Okay. So t is however time. Same thing for the other. It's going to be a, which is the radius, and 1 minus cosine t, where it is from negative infinity to infinity.
It'll be rolling forever.
Hmm?
It'll be rolling forever.
Yes. Alright, in Greek, brachtin means short time, and tashun is equal time. I don't know. I've never used those words before in my life. Okay, anyway. So, you guys learned some Greek right now. Anyway, so inverted cycloid, curve of the quickest descent. Okay, and see all particles reach Q at the same time. So when you have all three different ones traveling along the cyclone from different points, and they all equal at the same time. It's kind of like when you're watching one of those at the playground and you're watching the slides all going with different kids on it, and you notice at one certain moment, all of them are in the same rhythm. They're all at the same point at the same time.
The slides or swings?
The swings. Did I say slides?
You said
Yeah,
slides.
it's like
Oh.
slides.
Okay.
What kind of slides you got this in?
I know. Sorry. Okay, so the swings.
You're tired today.
Okay, the swings. You know what I'm talking about now.
Yeah.
The swings. Okay, it's like one of those things that like feel good on your brain where all of them line up at the same time, right? Am I just that weird little
Try
kid
not
that
to get
actually
satisfied.
patterns were satisfying to me?
No, for me it was when the swings make like a little wave.
We should take a field trip to the park.
Yeah, but we can't go to this park. You might get stabbed. Okay? Or
Any park around here.
I know any park around here. You know, you walk out of here with 3 stitches and 2 joints. So anyway,
Make it one.
I know, right? Okay, yeah. So, but when all the swings line up at the same time, that's what this is actually talking about here. When they come up to the same thing, even though they're traveling at different rates with the kids with different masses and different speeds on that. So as they go, they'll eventually line up at one point and then they'll change again. And so that's what this is when they all reach at the same time. So they're all lined up at one point. You guys got this in your notes. You can read it.
You wanna?
No, I don't, because I still can't even pronounce that. Okay.
Johann Bernoulli.
Sounds like a dinosaur.
And Blaise
Pascal.
Pascal. Pascal.
Pascal.
Calculus of variations.
This discovery
Sliding
was
packages
introduced
from a
into
loading
many
dock
famous
onto a ship.
mathematicians, including
Okay, there we go.
We're reading what is written.
Cycloid. Cycloid.
Or just a clock.
Why is it stated twice?
Why is it so bendy?
Why is it so bendy?
I thought those things are like.
Oh, yeah.
That's like a pendulum.
Yeah, but I thought pendulums were like solid. You know what I mean? Not like on a,
Oh,
a
yeah.
string.
It's artist's depiction.
Oh,
Christian.
I should know that.
To construct a pendulum ball that swings along an inverted cycloid.
Is this why your videos take forever to just these people talking?
His name is
It's like half of it is not even education.
Okay, yeah, this is educational.
Well, yeah.
two plates shaped like
We're
cycloids.
reading what is written.
Please
B.
pause here.
Is on a
and read
thin
it.
wire
Who
constraint.
knows? There's a
Okay,
bunch of like
anyway.
online viewers, you know?
All right, so it was informational stuff. You know, the reason why I talk about it. I put some more of that stuff later on in some of these next notes coming up too. All right, so I'm gonna give you guys the rest of this time. Please try these problems.
How much time do we have?
Start working on it. You got 10 minutes.